In our previous module of chapter 1, we have learned summation convention, contravariant and covariant vectors and the coefficients of the transformations. Now, in chapter 1, module 2, we shall learn the contravariant and covariant tensors, Kronica symbols and E-system, invariants and the higher order tensors. So, we start with contravariant and covariant tensors. So, first we learn about contravariant and covariant tensors. We know a bilinear scalar function T over V cross W is a mapping T from V cross W to F, where V and W are the vector spaces over same field F, such that T of Fx plus Gy comma Ha plus Kb equals to Fh Txa plus Fk Txb plus Gh Tya plus Gk Tyb. So, this is the definition of bilinear scalar function, where x, y belongs to the vector space V, A, B belongs to the vector space W, and F, G, H, K all are scalars which belong to F. Now, we consider a system by taking product of same vector space V called tensor product, denoted by this notation V. It is called tensor product notation V, tensor product V, or we denote it by V square or V2, consisting of a set of all bilinear scalar function on V star cross V star, that is the dual spaces of V, a binary operation in V star cross V star, say plus, satisfying T plus S of AB equals to TAB plus SAB, where Ts are the bilinear functions from V star cross V star to F, and AB belongs to V star, and an operation of scalar multiplication satisfying A T of AB equals to A TAB, where A belongs to the scalar field F and AB belongs to V star. By these two operations, one can also easily verify that this V2 is a vector space over F. Now, we take the basis vectors of this V2 and we define EKL belongs to V2 as EKL of EI EJ equals to del Ik del JL, which is can be expressed as a tensor product of Ek tensor product EL. We can show that this EKL form a basis of V2 and its dimension is n square, because V is of dimension n. So, the dimension of V2 is n square. So, elements of V2 are n square functions. Now, let T be an element of this V2, then we can express by its basis vectors in unbart system and also in bar system in the following way: T equals to TKL EKL, and that is equal to T bar Ij E bar Ij. So, T bar Ij E bar Ij can be written as TKL, and EKL can be expressed as a tensor product of EK tensor product EL. By the previous modules transformation rule for EK and EL, we get that the above expression becomes TKL PIK E bar I tensor product PJL E bar J, and which can be also written in this form, that TKL PIK PJL E bar I tensor product E bar J, or can be written in this form, TKL PIK PJL E bar Ij. Now, as E bar Ij is a basis of V2, therefore, T bar Ij can be written as PIK PJL TKL, because E bar Ij are linearly independent. So, we can express the previous expression in this form, that T bar Ij equals to PIK PJL TKL. Similarly, Tij for unbarred system, Tij, it can be expressed in this form, Qik Qjl T bar KL. So, 3 and 4 are the laws of transformations of the components of T from one system to another system. So, T is called contravariant tensor of order 2 or rank 2 or tensor of type 2, 0. Similarly, elements of V star tensor product V star are the covariant tensor of order 2 or rank 2 or tensor of type 0, 2. And the elements of V tensor product V star or V star tensor product V are called tensor of type 1, 1 or mixed tensor of order 2. So, we can define a tensor as follows: a tensor is an element that is a multilinear scalar function of the vector space formed by taking the repeated tensor products of the spaces taken from their pair V and V star, where V star is the dual of V. So, tensor is a multilinear scalar functional. If a tensor is defined at every point of a space, the field is called tensor field. So, we can define vectors and tensors in a n coordinate space Vn as follows. So, we are defining now the categorically how the contravariant vector, contravariant tensors, covariant vector and covariant tensors are defined is. So, contravariant vector is a set of n functions ai of the n coordinate x1, x2, xn are said to be the components of contravariant vector if they transform according to the equation this one, a bar I equals to del x bar I del x j a j on change of the coordinate system x I to x bar I, which This expression is followed from the module 1 also, but the coefficient matrices are the partial derivatives del x bar I, del x j. Similarly, A k can be expressed as del x k, del x bar I, A bar I. For example, we can take dx bar I, that is del x bar I, del x j, dx j. This is the differential of x bar I, and by this rule it can be seen that dxi's are the components of contravariant vector. Also, we can see that if f is a scalar function of coordinates xi, then df, which can be expressed as del f del xi dxi, is also a contravariant vector. Similarly, we can define the covariant vector in the following way. So, it is a set of n functions ai of the n coordinate x1, x2, xn are said to be components of covariant vector if they transform according to the equation a bar I del x j del x bar I a j on change of the coordinate system xi to x bar I. And similarly, from unbarred to barred, we can write this expression a k equals to del x bar I del x k a bar I. For example, we can consider this one, that if f is a scalar function of coordinates, then del f del x bar k, the partial derivatives of the function del f del x bar k can be written as del f del xi del xi del x bar k, and which follows the transformation law for covariant vector. So, partial derivative of a function is a covariant vector. Now, we come to the two symbols which are Kronica symbols and E systems. Both are regarded as tensors. A particular system of second order denoted by del I j, where I j running from 1 to n is defined as follows: del I j equals to 1 for I equal to j and 0 for I not equal to j. Such a system is called Kronica symbols or Kronica delta, and it can be easily seen that this del I j is an example of a mixed tensor of type 1 1. If we transform, we can see that it follows the transformation rule for the mixed tensor of type 1 1. So, del I j is a mixed tensor of type 1 1. And we can prove this one, that j and j tilde equals to 1 by the Kronica delta, by the help of the Kronica delta, because del x bar I del x bar j can be expressed in the form of del x bar I del x p del x p del x bar j, and that can be written as, the left hand side can be written as del bar I j, and if I take the determinant of this, so which becomes 1, where j and j tilde are the Jacobian determinant for the transformations from barred system to unbarred and vice versa. Now, we will also consider some systems denoted by E system, which are also considered as tensors. Eij, E upper ij, Eijk and E upper ijk, and they are called E systems. They are defined as follows: Eij equals to 0 or upper Eij equals to 0 for I equal to j, equals to 1 for even permutation of I and j, equals to -1 for odd permutation of I and j. Now, what is the meaning of this even permutation and odd permutation? So, if I see it elaborately, we can see this one, that for the first condition E11, E22 equals to 0, and for even permutations means it is coming 1 and 2, E12 equals to 1 and E21 equals to -1. For odd permutation it is E21 equals to -1. For 3 system, it is a 3 system, Eijk equals to 0 for I equal to j equal to k, equals to 1 for even permutation of ij and k, equals to -1 for odd permutation of ij and k. That is E123, E231, E312 equals to 1. This is called the even permutation of I and j and k for I, j, k 1 to 3, and E213, E321, E132 equals to -1. This is the odd permutation of I, j and k. So, E system and Kronica delta are also considered as tensor quantity. Now, we see some invariants. Any function psi of the n coordinates x1, x2, xn is called an invariant or scalar if it remains same after the transformation of coordinates. That means, psi equal to psi bar, where psi bar is the changed or transformed function when the coordinate system xi is transformed to x bar I. Note that if I make the partial derivative of this psi bar with respect to x bar r, then we can express in the following way that del psi bar by del x bar r equals to del psi del xs del xs del x bar r, which shows that del psi del x r is a covariant vector, which is also called gradient of psi or grad psi. So, the partial derivative of invariant is a covariant vector and which is called the grad of that invariant. Now, in our previous sections, we have seen the contravariant and covariant tensor and the expressions del ij, that the Kronica symbols, and the E system Eij and Eijk, that is E system for 2 variants and E system for 3 variants. Now, in this section we shall learn about the higher order tensors, its definition and the expressions how it transform. Now, in this section we shall learn about the higher order tensors, their definitions and the expressions. A set of n square functions Aij, because these Aij are the elements of V tensor product V. So, a set of n square functions Aij of the n coordinate x1, x2, xn are said to be the components of contravariant tensor of order 2 or of type 2 0 or also of rank 2 if they transform according to the equation A bar ij equals to del x bar I del x m del x bar j del x n a m n. So, this is the transformation rule for contravariant tensor of rank 2. For these are the components which transform from one coordinate system to other coordinate system. Now, similarly, we can express ARS equals to del x r del x bar I del x s del x bar j a bar I j. That means, this transform is from x bar I to x I. Similarly, for covariant tensor of rank 2, we can define in this way that a set of n square functions a I j is lower I j, a I j of the n coordinate x 1, x 2, x n are said to be the components of covariant tensor of rank 2 or of type 02 if they transform according to the equation a bar I j equals to del x m del x bar I del x n del x bar j a m n, when the coordinate system is changed from x I to x bar I. Similarly, from x bar I to x I coordinate system, we can express the covariant vectors or its components actually in the following way, that ARS equals to del x bar I del x r del x bar j del x s a bar I j. And again, for the mixed tensor, a set of n square functions, this is also a set of n square functions, that means a I upper I and lower j. So, that means these are the elements of V tensor product V star of the n coordinate system x 1, x 2, x n are said to be the components of mixed tensor of order 2 or of type 1 1 if they transform according to the equation a bar I j equals to del x bar I del x m del x n del x bar j a m n. So, this is the transformation rule for mixed tensor of type 1 1 when the coordinate system is changed from x I to x bar I. And similarly, from x bar I to x I system, we can write ARS equals to del x r del x bar I del x bar j del x s a bar I j. So, in general, we can define a tensor of type PQ in the following way, that the components of a tensor of type PQ is a set of n to the power p plus q functions denoted by in this way a I 1 I 2 to I p and j 1 up to j q of the n coordinate system x 1, x 2, x n are said to be the components of a mixed tensor of type PQ if they transform according to the law a bar I 1 I 2 I p j 1 j 2 j q equals to in the following way del x bar I 1 by del x m 1 dot 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 del x bar I p del x m del x m p and del x n 1 del x bar j 1 dot 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 del x n q del x bar j q a m 1 m 2 m p and n 1 n 2 n q. So, all these expression are the transformations of the components of the tensor of type PQ when the coordinate system is changed from x I to x bar I. In module 2 of chapter 1, we have learned the covariant and contravariant tensors of rank 2 and their expressions. Secondly, the expressions of Kronica symbols and the E system, which are also considered as tensors, and the expressions of higher order tensors, that means the tensors of type PQ and their coordinate transformation rules in this chapter. And so, this chapter ends with these two modules.